Thank you very much, George. It's indeed a privilege and an honor to discuss Professor Anderson's paper. Let me begin by saying it's impossible to be anything but impressed by the extremely wide-ranging scope of this paper. I think Professor Anderson is, his work is unified, a broad segment, perhaps the whole segment of such multivariate models which cover econometric models, psychometric models, factor analysis models, etc. Certainly he has unified the asymptotic theory, and by simply putting forth this general class of models, which I've deigned to call Anderson models, I hope that this work will open a door to a very interesting class of research questions. I am not nearly the expert in the breadth of this field of this breadth, so what I intend to do very briefly is to point out that the Anderson models include, as a special case, a class of models that I'm familiar with, a class of models that, at least in the normal theory, are amenable to an exact analysis and propose at the end the possibility or issue a challenge that perhaps a much larger segment of the class of Anderson models can be studied in even greater detail and exact results obtained. By the Anderson model, I'm referring to a model for covariances. I think that's the essence of the paper. S, the Wishart, the sample covariance matrix having a Wishart distribution depending with parameter sigma depending on a parameter theta. Theta is generally expressed in terms of lambda and tau in the paper, at least in the version I have. Sigma then is obtained as a linear combination of what could be nonlinear functions of theta. If theta appears in more than one place, in general we'll have possibly quadratic or nonlinear dependence. There's a special case which Professor Anderson did not get to, but I have, having the advantage of the paper, have singled out. The special case is what you can think of as a variance components model, where the covariance is a linear combination of specified symmetric matrices G. The coefficients theta, the unknown coefficients, comprise the unknown theta vector here. This is a linear model for the covariance. So I've given my subjective view of the class of Anderson models, the linear and the nonlinear. Now, there's a little bit of ambiguity here. It's possible by reparametrizing what I think of as nonlinear models, that is, models where theta here appears nonlinearly, reparametrizing them to put them into a linear form. And I think questions like that will merit further investigation. By the linear models, I mean the models that appear in this form. So there might be more linear models that will later be shown to be of that form. Of the linear models, those that are linear in both sigma and sigma inverse, that is, those matrices sigma of this form whose inverse is again of this form for the same G's, comprise a class introduced first by Professor Anderson, studied, I have that on the next slide, but studied by Seeley, Soren Jensen at Copenhagen. Those are the Jordan algebra models, and an important subset of those models are the reflexive or group symmetry models. These reflexive models include all classical multivariate models, those, for example, in Professor Anderson's book. The nonlinear models, again, it's apparently a much broader class, although, as I say, reparameterization might change that. And the question mark here indicates that I think there's a challenge in looking at this work on linear models, linear covariance models, and carrying it over to expose further the structure of the broad class. Just to illustrate very briefly what I know about the reflexive or linear models, reflexive subclass of the linear models, which have been studied by Steen Andersen, Hans Bruns, and Søren Jensen in Copenhagen, among they are the prime movers of that work. These reflexive or symmetry models have the following form. G, unfortunately a different G, sorry for the notation overlap. G, a group, is a symmetry group, a finite subgroup of orthogonal transformations, for example, all permutations of coordinates. SG, this will be a special kind of a special class, a subclass of the Anderson models, determined by the symmetry group G. It's simply the set of all covariance matrices sigma which are completely invariant under these symmetry transformations. Another way of saying that is that the covariance of G, for example, of G times X, for example, a permuted version of X, is the same as the original covariance of X. The claim demonstrated by Andersen, Bruns, and Jensen is that indeed all the classical multivariate models are of this special form. So it's quite broad in a sense. Again, in section 6.1 of Professor Anderson's paper, which you didn't mention in the lecture, he describes the model of independence, that is the set of all covariances which are of block diagonal form. That expresses the fact that the partitioned observation vector consists of independent pieces. Well, that arises as a reflexive or symmetry model where the group G consists of all block diagonal matrices, 2 to the n of them, with plus or minus identity matrices down the diagonal. If sigma is preserved under G transpose for every such matrix, sigma must have zeros off the main diagonal. So the familiar independence model is a special case. The complete symmetry model, a generalization of the interclass model, is a special case where we have the same matrix A in the diagonal blocks and the same B in the off-diagonal blocks. That's complete block symmetry. Just to mention others, circular symmetry models, dihedral symmetry models, which we're not familiar with. Actually, that's not true. In the literature, papers studying what they call the circular symmetry model really are studying the dihedral symmetry model. That is, it's the dihedral group that appeared in previous papers. Studying the groups lead to the proper nomenclature. Sphericity model, chapter 9 of Professor Anderson's book, the complex normal, the quaternion normal, which isn't so familiar to us, the model which expresses the fact that we have equal covariance matrices in N, or K I should have used, in independent populations. That, again, can be expressed in terms of group symmetry. All these reflexive models have very nice properties, assuming normality. That it must be, my comments are restricted to that case today. The maximum likelihood estimator sigma hat is simply the orthogonal projection of the covariance matrix S onto the set of symmetric matrices satisfying the G condition, which the key is the orthogonal projection. MLEs of means are orthogonal projections we're familiar with. In group symmetry models, MLEs of covariances are orthogonal projections, which leads to an analysis of variance of a sort for covariances. Exact distributions for maximum likelihood estimators for likelihood ratio test statistics, testing one model versus another, are also obtainable. Invariant tests, incidentally, for such hypotheses are based on, very simply, the characteristic roots of this residual matrix with respect to the sigma hat matrix. Finally, the challenge that I mentioned at the beginning is to look at the broad class of Anderson models, what I've just mentioned as a subclass, the reflexive case, which have very nice properties. Study the broad class of Anderson models, the nonlinear, some of which may in fact be linear under reparameterization. study the symmetries in variance properties of such models, I suspect that the Anderson class will lead to a very nice theory. Thank you very much.